Thanks a lot for coming. Welcome to my presentation, and I really appreciate that you choose this room. As testers, we have to test more and more functionality in less and less time, because successful software grows. We keep adding new features. We hardly ever are allowed to remove features. But unfortunately, we don't get more time to test more functionality, but paradoxically, we get less time because release cycles are getting shorter and shorter. So to cope with that challenge, we have to be more effective and more efficient as testers. And if we don't want to do more work, we somehow have to find more bugs in less time. And this is where test intelligence analyses come in. Test intelligence is a term for a bunch of analyses that analyze the data in your repositories. The version history, the code base, the test cases, the test coverage, your ticket information, your bug information, all that data, to help you find more bugs in less time by creating more transparency into the black box of software testing. To give you heuristics, to give you a gut feeling, to give you data where you have to do a lot of testing because the likelihood of new bugs is very high, and where we can maybe get away with less testing. And I want to both share the background and the research foundation and examples from practice. And before I start, if you have questions, please interrupt me immediately. Don't wait until the end of the talk, but ask me directly. The more interactive we get this, the more you take out of this. And I much prefer an interactive session than getting through the slides in the order I brought them. And it needs not be a well-articulated question. It's fine if it's skepticism or doubt, because testing is very different in different companies. And please interrupt me if you think that's not applicable to your context. Maybe I have another example. And we have a microphone, or just shout out the question. I will repeat it for the online audience. So what do I mean by bringing transparency into the black box of software testing? I have an example, a metaphor, that has nothing to do with software testing at first glance, to give a gut feeling of what I mean. You all know this? X-ray pictures. This is an X-ray picture of a knee. This is the kneecap. More specifically, this kneecap, after I unfortunately broke it in an accident a couple of years ago. And the bright lines are the wires that hold together the pieces of bone, and those wiggly lines are the clamps that close the scar. And I have this here as an example of very effective and efficient quality assurance, which might be surprising at first because obviously I don't mean the accident and the surgery from the same day. That wasn't effective and efficient, that was very unpleasant and unplanned for. But 2 weeks after such a surgery, you have to show up at the doctor who basically does QA. And what I found interesting was that doctor did not ask me where the pain was. He did not take a blood sample, he did not measure my temperature. In testing terminology, he did not retest all. Instead, he only took this picture and took a look whether the change that was performed by the surgeon matched the expectation he had of how my knee was supposed to look like. So I want to bring the same metaphor to software testing in this talk. And obviously, software has no 3D representation, so we can't do X-ray pictures. So this is where the metaphor ends. So instead, the idea is that we analyze the data sources we have in development and testing processes anyway, and crunch that data to answer questions that help us be more effective and more efficient. And the 4 questions I want to talk about today are these, and they are my agenda through this talk. The first one is, where were the most bugs in the past? Because sometimes there's a fundamental hole in our quality assurance process that lets a certain type of bug slip through more frequently, and looking into historic bugs can tell us that sometimes and help us understand that and close that to avoid future bugs. The second question I want to talk about is, where are untested changes? Because for long-lived software systems, untested changes are a very big source of bugs. That's the most likely area where bugs are to occur. Third question is, if I have more tests than I can execute in an available time budget, which ones should I select? I don't know, those of you who were in the keynote yesterday by Paul Holland and his colleague, he mentioned that he had 47 hours of automated tests for the daily test, which is hard to squeeze into 24 hours. And one solution to that problem is to not always execute all tests, but select a subset and execute that tiny subset more frequently. And it makes a lot of sense if the tiny subset finds a large percentage of the bugs. And I want to talk about these approaches. And the last one is, I mean, we read so much about AI. Many of us use it in our daily life, sometimes at work. And there's a lot of research on predicting bugs. Where will bugs occur after we release software? And maybe if we know where they will occur, we can do something before we release to keep them from occurring. And this is the last question I will talk about. So that you can place where this experience come from, some background on me. I have two roles. I work as a researcher. This is how I looked when I started my PhD thesis in Munich. This is how I looked when I finished it. And I've been told it mostly shows that there was always enough food available when I did my PhD. But I want to make a different point. The point I want to make is that I still look at this topic from both perspectives. As a researcher, I'm interested in what is really relevant to measure, because unfortunately we often measure what's easy to measure and not what's relevant to know. And as a founder, I'm interested in impact, because just by stepping on the scales every morning, I don't lose any weight. And just by having analyses doesn't improve our software quality. So in the founder role, I'm interested in how does an analysis need to look like to really lead to better software. And we incorporated the company 15 years ago. We are 62 people. 23 of us have a PhD in software quality analysis. So what I share is not only from me, but from the colleagues as well. Last slide on background. This is some of the companies we work with. And the key point I want to make is, obviously, software that runs in an ECU in a car looks different, and the test process looks very different from software that runs maybe in C# in an insurance company or written in COBOL and runs on a mainframe. But if you take a step back, all those companies have the challenge that they must test more and more functionality in less and less time, and it's useful for them to have these analyses to find more bugs faster. So, before we can start with analyses, I have to get us all on the same page with the data. And I skipped over version history and tickets. Version history contains the code base and all changes everybody does on any branch to the code base. And ticket contains, like in Jira or in Azure DevOps, contains bugs, features, and so on. And I guess you are more or less familiar with that. But from my experience, what people understand under the term of test coverage varies a lot. So I want to quickly talk about what I understand of it to get us all on the same page here. This is an open source Java system called Pixelitor. It's much like a very simple version of MS Paint or Photoshop. So you can draw bitmaps with it. And I like to use that for some of the analysis in the talk. And this is a method from the Java source code of Pixelitor. I don't expect you to read it, but the key point I want to make is this is one method, and we ran unit tests against that and used a so-called code coverage profiler to automatically capture which code was executed by the tests. And in green, you see the code that was executed, and in red, you see the code that was not executed. And the typical way I see code coverage profiling used in practice is for automated unit tests only, for the purpose of seeing if we tested what we expect to test. So the typical use case is, okay, here's something red. Obviously, we didn't go into the if. And then as a developer, if I write a unit test, I ask myself the question, should we have gone into here? And if so, should we write another unit test? And there's nothing wrong with this use case. It's just very limited. So in this talk, I want to make two differences. The first difference, I want to talk about the entire system. And the second difference is we also use coverage profiling for all different types of tests. For end-to-end tests, for integration tests, for manual regression tests, for manual explorative tests, and so on. So what do I mean by this? To talk about the entire system and to give you a gut feeling what the data these analyses looks like is I need a visualization called tree map. It's very simple. This is a visualization of the source code of Pixelitor. Every rectangle corresponds to a component of Pixelitor, and the bigger the rectangle, the larger the component in lines of code. Now we zoom in. Components are still in place. The smaller rectangles now are files. And if we zoom in further, every tiny rectangle now is a method of the Pixelitor source code. And it still holds. The bigger the rectangle, the bigger the corresponding method in lines of code. And now I can use this tree map to look at code coverage. All the rectangles that are green are methods that were executed by the automated tests of Pixelitor. And everything that's gray was not executed by the automated tests of Pixelitor. So if we introduce a new bug somewhere in one of the rectangles, if it's a green rectangle, there is a chance that an automated test finds that bug. If it's gray, there's no chance that an automated test finds that bug. And the second point I want to make, we can also capture test coverage for automated tests. The coverage profiler doesn't care about what type of test it measures, whether it's an automated unit test or a manual regression test. Here we run Pixelitor, do a manual test case, and on the right-hand side you see the code that gets executed while that functionality runs. So, enough basics. The first question I want to talk about is, where were the most bugs in the past? And I have an example from practice. This is an industrial commercial software system. And the tree map is the source code base. Every rectangle is a file. And the darker the color blue of that file, the more often that file was touched during bug fixes in the last 3 years. So that means, more or less, the darker the color blue, the more bugs were in that file that were fixed in the last 3 years. And if we look here, the first thing we see is that the biggest file has the darkest color. That's actually not so interesting. If we know nothing about where bugs are, we can assume them to be equally distributed, and then the biggest file has the highest likelihood of having bugs, so that's not interesting. But if we look here, we also see that the entire area here is much darker and thus contains more bug fixes, and this is a good approximation for more bugs than the entire rest of the system. So what happened here? To better understand this, we measured the coverage of the automated tests of that system. So the darker the color green, the higher the line coverage of the automated tests. And you've already noticed it. If we put two maps on the same page, you see such a coincidence. The area where most bugs occurred, there's the least coverage of automated tests. Now, what I forgot to tell you was that the data we used for this analysis only used bugs that were reported by the users from production. So not the ones we found during testing, only bugs users reported from production. And we see that a lot of them slipped through. And with this data, we went to the development team and asked them, and the testing team, and we asked them, how can this happen? And what we learned is this. On this side is backend code, Java. On this side is backend code in Java. And this in the middle is front-end code in JavaScript. And interestingly, the same team wrote the automated tests for the backend and the front-end code. And for both areas of code, they had the guideline that whenever they did a change, they needed to write a test for that. And it worked quite well here and didn't work at all here. And what happened? For the backend code, it was easy to write new automated tests because the foundation had been laid to make it easy to write automated tests. Not so for the front end. But this makes it very transparent that this is a bad idea from a quality assurance perspective. So for the next sprint, they allocated time to lay the foundation to write automated tests, to make it easy to write automated tests for the front end. And when we repeated this analysis years later, we saw a different picture, and there was no such glaring hole in the quality assurance process. So instead, they had coverage here as well, and the defect density was not surprising in this area. So before I go to the next question, any questions or comments on this analysis? Yes, Stefan.
What about
Do you have anybody has a microphone? Perfect. Stefan.
what about these squares that are green and dark blue at the same time?
Good question.
What about that?
What about the squares that are green and dark blue at the same time? One explanation would be that there was a bug, and then they wrote an automated test to make sure that this bug does not occur again. And then when we took the data, we only took the coverage from the latest revision, but they still have the historic bug fixes here. Another explanation could be that they did have a test, but it did not find that type of bug. Thanks for that question. There was another question. Okay. Further questions or comments? Then let me continue with the next one. So we saw in the large that if we add new code and change code and don't have automated tests for that, it's a bad idea for quality in production. And we can actually look at that on a much smaller scope as well. And there's a lot of research on that. There's a whole area called defect prediction that looks at software before it gets released and correlates all types of stuff we can measure using machine learning with bugs reported from the field. And the unsurprising result is, for long-lived software systems, most bugs occur in those areas that changed since the last release. Such a surprise. Now, what surprised us is how many code changes still slip through testing unexecuted and are shipped untested into production. And I have an example for this. This is another industrial software system written in C#, 1.5 million lines of code. Again, each rectangle is a method. And gray means not changed since the last release. Orange and red is modified in new code. And in this system, 30 people worked for 6 months. This was prior to Agile transformation. Now they release much more frequently, but back then they released every 6 months. And we see a lot changed on the right-hand side, much less changed on the left-hand side. So if we don't have enough time to test everything, we probably want to make sure that we test especially thoroughly on this side. This is the coverage of the testing efforts. And this is already the aggregated coverage of a lot of different test types. Gray means not covered during testing. Green means covered during testing. And here we have aggregated automated unit tests, automated end-to-end tests, manual regression tests, and manual explorative tests. So now the interesting question is, on the one tree map, we saw the code changes. Here we saw the coverage. How does this combine? And this is what we see on this map. Gray means unchanged since last release, because empirically we know there will be less bugs here than in the changed area. All the colorful stuff is the changed and new code. And only if it's green was it ever executed during testing. And we took this picture the night before the planned release. So here's entire components, tens of thousands of lines of code that were not tested at all. They slipped through testing completely unexecuted. And how do we interpret that? If it's green, it's hard to tell. It could be that we found the bugs that are in there. It could be that the test passed by that and didn't find the bug. It's, as always in testing, we can never prove the absence of bugs. But the orange and red stuff is very easy to interpret. We can't have found a single bug in there because we never executed it. And the key idea of this analysis is to offer a conscious decision whether we want to ship like this or not. Because it could be that it's not a problem if the functionality doesn't work now. Maybe it's end of year stuff, end of business year, and maybe our business year ended in September, and we know we don't need that component until next October or something, or next August or something. But this was not the case here. So here they decided this is all stuff they built for the new release because they need it in the new release, and they postponed the release to do additional testing to close those gaps. Yes, question? the question is, was there any manual testing done? Good question, yes. Actually, there was one team that did manual regression tests of old functionality, and there was another team that wrote automated tests for new functionality, and the team that wrote the automated tests failed to deliver automated tests on time. And so that's unsurprising that the regression tests only tested the old stuff and not the new stuff. And so what they did was they postponed the release by 3 weeks, and they didn't have time to finish the automated tests, so instead they did a lot of explorative manual testing of the new stuff. After this. Thanks. Here's another question. So let me repeat the question. If in your team people make a change, it gets tested before it can be released. Correct? Yes. Excellent point. Let me take that as a transition for the next slide, because that's how we use it as well. This shows the entire system, and if your role is responsibility for the entire system, or if you decide, can we ship like this, this is the right view, but for daily work it's too coarse-grained. If we use it in our own development, we use it on the level of individual issues or tickets or bugs or feature requests. And then you can see the tree map only for the code that was changed during the implementation of that ticket. And we have the same guideline. We can't merge a new feature, a new ticket. We can't close an issue if there's still untested changes. Or more specific, if there's still non-trivial untested changes. If it's just a getter that reads one single variable, or it's a setter that writes one single field, it's fine if there's not a test for that, because we know the code is so trivial that if we review this, it's enough to know it works, but for everything more complex, there needs to be a test. Either a manual test that has been performed, or ideally an automated test that we can add to our CI. Thanks for that question. Further questions on test gap analysis? There's one question. Good question. Let me repeat. Can we prioritize that if there's not enough time to test everything? And actually, if you're in such a situation, and we've seen this often in domains where you're not forced to have 100% code coverage, then there usually is not enough time to close all test gaps. So you must prioritize. And our experience is that the best level of abstraction to do the prioritization is not the code level, but the feature or ticket or issue level. Because the code is more distant to the actual functionality than the ticket. So we now, the groups that we work with that use these analyses tend to do the prioritization on the ticket level, and then only focus on the ones that are most critical from a certain perspective for that test phase. Thanks for that question. Last question before I continue. Can you maybe get the microphone?
Do you take call hierarchies into account as well, measure coverage? Do you take call hierarchies into account? So if I have a lower level component that was changed and I retested my bug from an upper level component, it doesn't make sure or does not provide any information about how the changed component would behave if it is called from another component. So is this call hierarchy considered as well in here?
Yes and no. For such an analysis, we do not consider the call hierarchy. What we do is we capture the code coverage for every single different test type separately. So you can, if you want, you can only look at the code coverage for the unit tests, or the integration tests, or the manual tests, or the aggregation. But we have other analyses, for example, code dependence analyses that can use the call hierarchy or other dependencies between code units. But our experience is if we use that dependency information here for test selection, if we want to know, if we want to test one bit which tests are affected, then you typically, with very few changes already, you select all the available test cases. And then you don't gain a lot in practice. And what we're really after is the gaps. And if it was not executed at all, we don't need to consider call hierarchies, because if it was not executed at all, we know through none of the different call hierarchies was the code reached. Thanks for that question. Let me continue with the prioritization question, because I think it's a good fit to both your question and your question. So the next one I want to talk about is, if we have too many test cases to execute all of them, which subset could we run more frequently to find a lot of the bugs in much less time? So the idea is we don't always run all tests, but we select a small set which we run more frequently, and we still sometimes run the entire test suite. But if we select the tests in a clever way, then in a small amount of time, we can still find a large amount of the bugs and just shorten feedback cycles. And we work with a lot of development and test groups that have tens or hundreds of thousands of automated tests, and they run tens of hours or hundreds of hours or even weeks if you would run them all one after another. And this makes it very painful if you break something until you learn that you broke that. And it's important to cut the feedback time short. And there's a lot of approaches, and I want to show one very simple approach and then summarize other approaches. And for this, I want to return to Pixelitor, the paint program we had at the very first. And now we look at one single test case. It's called test Gaussian blur. This Pixelitor has a lot of blurs, and if you look at the manual test cases of it, there's a test case for each of the blurs. And every method that's green here was executed during the test Gaussian blur test. And now imagine we execute the test suite, and the second test we execute is called motion blur, test motion blur. And now everything that test executes that was not tested previously by another test in the suite is green, and everything it tests that was also tested before by the Gaussian blur is blue. So we see it does add some new code coverage, but most of it was already tested by the other blur, which is not surprising because it's also called blur. So it does a similar thing. The third test in the suite is called lens blur, surprise. And you notice that there's still some green bits, but most of it is blue. And for time reasons, I cut this off now. There's a lot of other blurs. So if we take a step back and pile up the green bits to the right, you see diminishing returns. The first test adds a lot of coverage, tests a lot of code that contains bugs. And then there's a lot of similar tests that add little new coverage. And the Pixelitor was an illustrative example, but I have an example from a customer from the medical software field. This is a test suite for a dialysis system. It runs 48 hours. And on this axis, you see the test coverage. And what we see, there's a lot of plateaus. And each plateau is a cluster of very similar tests, like the blurs. And the first test in a cluster adds a lot of coverage, and then you basically spend a lot of time in that plateau. And if we now would cut off this test suite here, then in a couple of hours we would only produce 20% of the coverage that the entire suite finds. And so we can't expect to find more than 20% of the bugs that the entire suite finds. And the obvious idea is to order those tests in a more smart manner, to prioritize those tests in a different way than the default sequence they occur in. And there's a lot of research, hundreds of different approaches, and our master student and bachelor students and PhD students have implemented a lot of them. And the heuristic we found that works best is this. It always executes that test next, that per second of test execution covers the most lines that were not previously tested. So if we run that approach here on the Pixelitor, the first test it selects is called create and modify selection. The second one is test change view settings. The third one is second layer. It's not important what they do, but you notice it's not blur, 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 but very different names of tests already. And if we step back, you see the same amount of tests that roughly take the same amount of time to execute, produces way more test coverage than previously. And coming back to the real-world example, it turns this chart into this chart. So if we cut off here in 8% of the time, we already produce almost 100% of the coverage. So this approach works well because it removes redundancy from the test cases, from the test suite. Because most of the test suites I've seen in practice, especially if it's end-to-end tests, have a lot of clusters of similar test cases. And they run through the entire cluster before starting with the next cluster. And a good approach to optimize that is to cluster the test cases and then select a single one from each cluster before we execute the second test from one cluster. And I've done one trick. I've always spoken about optimizing coverage, but what we really want to optimize is fault-finding capability. And I'm acting as if coverage is a good proxy for fault-finding capability. And for these analyses, where we use coverage not as an optimization goal for testers, but to automatically select tests, it actually is. So we've done a lot of empirical research, both with historic bugs in open source systems and using mutation testing, where we insert synthetic bugs. And through all the different systems we analyze, on average, in 6% of the time it takes to execute the entire test suite, we find 80% of the bugs, and in 11% of the time, we find 90% of the bugs. Obviously, not 90% of all the bugs, but 90% of the bugs that the entire test suite would find. Question? Joao?
Have you ever considered looking at historical data for tests, the tests that fail most often?
Let me repeat the question. Did we look at historical data to select those tests that fail most often? Yes. That's also another approach, and you can mix it in. But our experience is that this works better if you want to optimize the smoke test suite. So the typical use case for this is you have a large test suite, and it's very expensive to execute. And you want to make sure that the code, the software under test is good enough to go into the expensive test. Because if there's one fault that makes 1,000 of 20,000 tests fail, then this one fault hides all the other faults. And then this is a good approach to optimize the smoke test suite that has to pass before you go into the entire test. You can also combine it with your suggestion that you fill some of the smoke test suite with this and use maybe the 10 historic bug failures, or the 10 most frequently failing historic tests. Thanks for the question. Maybe before we do other questions on this, let me wrap up this topic. There's two primary use cases we see teams using test selection in practice. The first one is smoke test optimization, what I just covered. And the second one is change-based selection for the continuous integration pipeline. And the basic idea is every time you run tests in your CI, you select those tests that match the changes that were performed since the last test execution best. And now there's a load of different approaches for test selection. I just spoke about something we call Pareto optimization with the tree maps for the pixelator. And there's a lot of different ones. And here's also where we see AI-based approaches coming in. For example, one of our students uses large language models, and it makes them produce embeddings for test cases to cluster test cases. And this actually works quite well. On the other side, there's test impact analysis, where you select tests based on which code they run through, or predictive test selection, where machine learning is used to correlate changes and historic test failures with test cases. So that over time you learn which tests tend to fail when certain amounts of areas of code are changed. Or information retrieval, where you have techniques much like a search engine. And the key buckets I like to put them in is those are coverage-based. You need test case-specific code coverage for these approaches. And those are not. They use different approaches just on the test content. And this is the precision and effort direction. By this I mean it's much easier to employ approaches that don't require test coverage, but they don't produce as good results. So depending on how big the pain is, all of these approaches might have a valid cost-benefit ratio. So if the pain is large in the sense that the tests take very long, it might be justified to take the time to measure the test coverage once, so that you know where which test case runs through. If the pain is not so big, maybe these approaches are good enough because they take less time to set up. Questions on test selection? Joao.
Just another thing that I don't know if you've ever considered this, but with the approaches that you were showing, I'm imagining that if I have a bug and there are two tests that are going to catch it, there's a big smoke test, like an end-to-end test, and there's a unit test that will tell you exactly what's going on. With that approach, you're going to see the big one failing first, or being the one that gets selected to run and find the bug, but it's going to take you way longer to understand what's happening because it's a big test and you don't know exactly why it's failing.
Good point, and it depends. Let me repeat. If you have different tests that can find a bug, then a very fast unit test might be prioritized to the back because it covers less code than a slow but large test and end-to-end that covers a lot. That depends a lot on the heuristic you use. If you use a time-based heuristic, then the unit test might even be upfront because we select the tests by the lines of code per second of test execution they cover. If you leave that away, then you're correct. Then you select all the big slow tests that are hard to debug and squeeze out all the unit tests. But this is the approach, and there's a lot of test selection approaches that propose this, and we don't think they are a good idea. So we always use time-based metrics.
A question from our online attendee. When you were talking about the test impact analysis and all those other test selection approaches, I was asking if you have a tool to recommend to do this analysis.
We built a tool, so I'm very biased. Our tool has these analyses, but there's other tools that do them as well. Actually, I think there's few tools that are production ready that do this. So I can put the name of our tool on later. Our booth is also out there, but I don't want to do advertisement for our tool on stage, so I hope you accept if I don't talk about our tool a lot here.
You can also answer the questions of the attendees online.
Thanks for the question. So last part. Can we predict where errors will occur? And actually, there's a huge research community that has been doing this for decades. And as a researcher, many people, me included, were envious because there's one research group with a researcher around Nachiappan Nagapan, short Nachi, who received a Best Research Award every year for basically doing the same thing. Because he's at Microsoft Research, and you remember when your Windows PC crashes, it telephones home and reports the bug. And he sits on those big bug report databases for Windows, for SQL Server, and so on. And every year, his PhD students correlate other properties of Microsoft software with bugs, and then he has a new research paper how to predict those bugs. And surprisingly, so his key result is, and has been replicated by other groups, that 80% of the bugs are in 20% of the components. And that sounds like we can find 80% of the bugs with 20% of the effort, which would be great. Unfortunately, Nachi never reports the size of the components, and nor did most of the other researchers. And that's a problem because components are not equally sized. This is our own code base, and you see components have very different sizes, and this is typical for most systems we analyze. And if we just look at the 10 leftmost components and order them by size, then the two biggest components have 85% of the code. But if defect prediction would do this, then it would predict 85% of the code contain 80% of the bugs. And that would not be very useful because that would not save us any effort. So, but this is actually what happened. There's a research competition where you can enter defect predictors, and a guy from Bremen, Thilo, he entered a defect predictor that only sorted components by size, and he won the competition. So he basically showed, in a somewhat offensive manner, that all the other approaches use very complicated defect prediction, very complicated machine learning to sort by size. So that's not interesting. So what we looked at is, can we use method-level defect prediction? So not component-level defect prediction, but instead method-level defect prediction, because our methods don't vary in sizes greatly. And for that, we trained machine learning models on historic bug data to predict those bugs. And then we compared it against, did we really have bugs in production after the release? So this is the setup. We reproduced some of the most highly rated research work. We trained it on our historic releases, and then we looked at the different years, what bugs had our customers reported, and were they really in those areas. And our student Florian, he analyzed 2 releases, and he analyzed 50 defect-prone methods each. And now the interesting question is, how many of them were really defects? Because as a developer, if a tool comes and tells me, through some machine learning, this is probably defect-prone, but I can't tell you why. I will only accept this as a developer if there's a high likelihood that this is really true. So maybe 40 out of 50 or 35 out of 50, because I probably won't find all the errors. So after reading all those papers that won the research awards and training our defect prediction model, and him working through the 100 most defect-prone methods, in some he had 0 bugs. So that's very frustrating. What happened? Does it not work? Or were we simply too stupid? It's a valid interpretation as well. And to our defense, there's other scientists who have done the same thing. And Bacchielli and his colleagues showed that, sorry, I didn't translate this, defect prediction is not better than random classification. And this year, Reed Holmes and his colleague showed that method-level bug prediction is extremely poor, or to put it more positively, they said it's an open research problem, which means that we don't know how it works at all. So even though it sounds like it would be a great thing, we haven't been able to get it to work. Other researchers I highly look up to, like Alberto Bacchielli and Reed Holmes, they haven't got it to work. So I think with everything we know about AI and defect prediction, it simply does not work yet. So I just wanted to include this in here because while it's very impressive how many LLMs work, it doesn't help for this. Let me just wrap up what I wanted to show before we take a couple of minutes for questions. The data in your repositories can help us find more bugs in less time. But test intelligence analyses are a toolbox. For those of you who were in the keynote yesterday evening, there's not one principle that applies in every single context, and it's the same thing with test intelligence analyses. They must be fit into your context, and you won't be surprised that I'm happy to help you and talk through your context if you're interested in this. Jakob and I will give a demo of our own tool. That's the name of it at 4. And we have a booth outside here where we will be here tomorrow, today, tomorrow, and the day after. And thanks a lot for your time. I think we have 2 more minutes for questions. This is the link to the slides, and I'd be happy if you could rate me, both positive and negative. I'm always happy to learn. There's a question back there.
Actually, thank you very much, Elmar, but if you could prioritize this question that you got from an online crowd, and then the people in here can always grab you after the talk. So we have been asked, what would you do when it comes to a legacy system that does not have unit tests?
Good question. I guess I would plan to write some, but that's probably not the answer you were looking for. From our experience, the test gap analysis is something we see teams introduce that have a very low level of automation to help them focus on those areas that are the most error prone because a lot of changes occurred there. And second, this analysis where you look for where were most bugs in the past is also completely independent of how your testing efforts are actually, how your tests are actually performed. Thanks. Last question.
So for defect prediction, have you ever considered, or do you know about research where the person who does the commit is considered for the defect prediction?
Yes, excellent question. There's a lot of work by Andreas Zeller from, he is now in Saarbrücken. And he, amongst others, analyzed the Eclipse system, the big open source IDE. And he actually reports that there's one person, if that person does the commit, it's very likely that there will be a bug. And now the interesting bit, that person is Erich Gammer, the founder of the project, the most renowned architect of it. And so what does that tell us? There's two interpretations. One is Eric is too stupid, and the other one is he only does the difficult stuff. And I found that interpretation much more likely. So you can't use that analysis to say we should fire those that are the most bug prone, but maybe it tells you, but you probably knew that before, that Eric only does the difficult stuff, and that it makes sense to test that then. Thanks for the question, and have a nice lunch.